It has begun.
It has begun.
Okay, so kind of a cool thing happened today. It's well.
I'll get to hear this twice.
You get to hit this twice. Okay.
So,
So
Grade Y.
you might see it on the news or someplace there. So then at Andover Middle School today, there was an award ceremony for a teacher who won. It's called the Milken National Educator Award. And so this was established by a guy by the name of Lowell Milken back in the mid-90s. And basically, it's called like the Oscars of teaching. And so what this organization does is that they find, typically in a given year, about 100 teachers from across the nation. And they actually like go find you. Like you don't apply for the award, they go find you.
Wow.
And everybody's like sworn to secrecy and all this good stuff. And so I won this award back in 2005. And that's what this gold pin is. And so it's cool because they have this whole assembly and they you get the gold pin and they also give you $25,000, which is
solar phone.
well, no, I had that back in 2005. Okay, that money's long gone by now.
Nice.
That money's long gone. Bought me a nice Honda, okay? Of course, it got traded on a Toyota truck. Anyway, so that money's been recycled. Anyway, so it's kind of like the mafia because.
Eh?
Huh?
Eh?
Oh, yes, it's like the mafia. So it's like once you've been made, then you're in the club, and so they let the former teachers that have already won it. They let them know that hey, like they'll send out an email that says hey, if you can make it, go to Andover Middle School today, and we don't know who won it, but we know that somebody there did, and it's kind of cool because you know the gig and you know how much they're going to win and all this good stuff. Anyway, so it's kind of cool. And so like I said, I won mine back in 2005, and anyway, so it's a cool deal. So if you see it on the news or sometimes it'll be on Twitter or something like that. So like this year, like they typically give out 100. For like the entire United States. So it's kind of cool if you're like one of those 100. If you consider like the odds of all the teachers in the United States. So it's kind of cool. So anyway. All right. Any questions on the multiple choice part? Bruce, did you have a question?
No, I was just wondering if we were going to go over it.
I can't. Well, that's usually implies that does somebody have a question.
I mean, I just wanted to.
right?
How come, which one? Talk to me, man.
All the following.
I'm not going to go over all of them.
I want to know.
Yes, what are
Just
they?
ask questions.
You'll find out when
about
he
all
grades
of
them.
Okay, you asked question one.
It's indirect hint, the answer to number one.
The indirect hint
Yeah.
on the answer to number one.
It starts with zebra.
Comic Sans.
It does involve an F.
Where?
Ooh.
Okay.
Oh. It has a number
No,
too.
just the thought
And it involves
of Comic
a
Sans.
2,
Okay.
Let alone there is
but not a square root of 2.
not.
So
Oh,
Were you
now you got
trying to put
50-50.
something in my mind? Because there's
Comic
nothing.
Sans.
There's nothing.
I'm not
You have
changing
no
my
reward
answer.
into the font.
Okay,
No,
well,
I'm
let's
fine
talk about this, all right? Because you're talking about a pendulum, and the period of the pendulum, and this is what's on your equation sheet, is 2 pi L over G. So the frequency is the inverse of that, which would be 1 over 2 pi times the square root of G over L, okay? So you're told that Bob of mass M, now here's the deal, and this is going to be important. Does the mass of the bob at all impact the period of the pendulum?
No.
No, they didn't. They talk about the mass of the bob, but the mass of the bob,
See where they.
yeah, isn't important. Okay, because it's not a factor in the equation. So the only thing that affects the period of the pendulum is how long the pendulum is in the gravitational field. Okay, that's it. There's nothing else. Okay, the amplitude, not a factor. The mass of the bob, not a factor. Okay, so if you look at what's happening, then it says, okay, now a bob of mass 4m, which again doesn't make any difference at all, to a rod of 4L. So again, there's two ways that you could do this. If you like smash mouth physics, you could come in here and plug in G, make it 10 meters per second squared. Make it simple. Let the initial length be 1 meter, okay? And you could go through and you could calculate that frequency. Then you could come in and say, okay, I'm going to keep G the same, but instead of having a length of 1 meter, you're going to have a length of 4 meters. Now, think about this. As this length gets longer, what's going to happen to that frequency? It's going to become
Smaller.
You're going to be dividing by a bigger number. So what's going to happen to the frequency? It's going to go down. But then what's going to happen to the period of the pendulum? It's going to go up because these are inverses of each other. So that's the smash mouth way to do it. Okay? Put in the numbers and make a comparison. The more elegant approach is to go, okay, that's 1 over 2 pi times G over L. Okay, so that's my initial frequency. So then my new frequency is going to be 1 over 2 pi times the square root of G over 4L. Okay, so since all of this is underneath the radical, what could I do? Could I rewrite this, wait for it, as the square root of 1/4 times the square root of G over L? Legal? Very much so. So what's the square root of 1/4?
1/2.
1/2. So if this side gets reduced by a half, what has to happen to the frequency?
Gets reduced by 1/2.
It gets reduced by a half.
I got the right answer.
Hey,
Okay.
take that.
Number 3 is also going to involve a 2. Okay? There might be a radical, there might not be. Keep in mind on number 4 that there are 2 springs. Okay? Not just one, but there are 2 springs. I will tell you this, out of all of your answers on these 8 questions, you should only have 1 A. There should only be 1 A out of all of your answers.
I don't think I only have one way. I don't have it. I turned it in yesterday. So
All right, anything else? Are we good? Once, twice, sold.
now now it's banana time.
We're good.
Okay, we're good.
We don't say that name.
Compare it to Dawson.
Don't say that name.
Mr. Bergkamp, a couple days ago, we were in scholarly school practice and we had a question. We had physics as the category for some of the questions that we had. But it was electricity and magnetism.
Which we have not done yet.
We have that done yet.
We should have gotten over it.
Yep.
I am calm.
No, you're not.
This is me being calm.
Be extra calm. I don't doubt it. I said less hysterical.
I am more calm.
Most calm.
This is me being the most calm.
I am the most calm.
Okay, no.
We know that. Until I study math.
Wait,
No.
where's Cool Tape? He was here earlier.
He's at a swimming.
Ah. Oh, that's why.
That's being fun.
Tape?
Why you have to
No.
make butter?
Stop.
Mixes it with
I'm almost to the middle of my notes.
bone butter.
Bone butter.
I have
That makes bone.
It's like,
And I also made it in knuckles. I need my
12 more pages to go.
How?
So we have to go over 12 more pages of information.
How many pages?
How much sausage can I put in my? You know this.
Actually, a lot. If it's mixed in correctly. Because if you just dump a pile of sauce in food, they're gonna notice.
18.
But if it's mixed
Okay.
in the food well enough, then
So here's kind of a summary
Oh,
of
my.
where we're at so far in terms of energy of the spring, okay?
Wow.
So if this thing is oscillating, it's simpler if it's a horizontal oscillation, but it's also true if it's a vertical oscillation. But when you talk about these two types of energy, okay, and when you can set them up to the max. So if you're talking about just the potential energy stored in the spring, a generic way to calculate energy stored in a spring is just 1/2 kx squared, okay? That's it, 1/2 kx squared.
Wow. I'll stop now.
Now, if you're at the maximum, okay, where A is going to be this amplitude, it's the exact same equation, but the only difference, instead of saying 1/2 kx squared, we're going to substitute in here 1/2 ka squared. So it's the same idea, it's still a distance squared multiplied by your spring constant. But if you know it's all in one form of energy, where you're at that maximum elongation, you can set that equal to 1/2 ka squared. Now, the same thing is going to be true of your maximum kinetic energy. Where is your maximum kinetic energy going to occur? Where is that bob or mass physically going to be?
At the equilibrium point?
Yeah, in the middle of that transition point, okay? So your K max, and this is where these are like opposites. So your K max is going to occur in the middle of the oscillation. Your U max is going to occur at the end of the oscillation. So if you're at any other point other than the middle of the oscillation, then this is going to be 1/2 mv squared. Just like if you're at any other point other than the maximum elongation, this is going to be 1/2 kx squared. So you can only set this 1/2 ka squared if you know, hey, this is as far as this thing is going to go, or this is when it's at the middle of the oscillation. So then what you can do is a little bit of voodoo. And you can say, okay, so there's actually like 3 different ways you can express the total energy of the system depending upon what you've got. So if you're at a maximum elongation, the energy of the system is just going to be 1/2 ka squared. If you're at the middle of the oscillation, where there's no U and it's all K, then you got 1/2 mv max squared. At any other point within that transition, it's going to be the sum of some kinetic energy plus some energy stored in the spring. So don't flip out and go, oh, this equation is different from the energy in the spring. It's the exact same equation. You just use A when you're at that maximum amplitude, and you use Vmax when you're in the middle of the oscillation. And if you're at any point in between, it's just 1/2 mv squared plus 1/2 kx squared. Okay? Good with that. Okay, so I just don't want you to go, wow, there's all these weird equations. They're not weird equations. It's the same equations that we've dealt with. We just kind of repackage them a little bit, and that's it. Okay. So, with that said,
So
Let's-
like chips.
huh?
So like chips. There's ruffled chips and there's wavy chips and there's ridged chips, but they're all basically the same
Kettle
thing.
cooked.
Just
They're not the same.
those are different things.
Okay.
Kettle cooked.
They're basically the same thing, just in different packages.
Doritos.
Technically, there's a bit of difference in texture between wavy ones and ordinary ones.
Rippled, ruffled,
You
and wavy.
said wavy, ruffled, and rich.
Yes.
Those are all the same thing. They're just different branding.
Yeah. Same thing, new package. Same price too.
They're competitive, that's why they have the same price.
So, that's kind of, speaking of kind of repackaging the same chip. So, let's say that you've got a spring and you're going to try and find that spring constant, right? So assuming that you're within a gravitational field, which we are. So on a this is going to form this linear relationship, otherwise known as Hooke's law. Okay, so unless you're told differently, springs always obey Hooke's law, unless you like completely stretch them beyond the limit. So because this is a linear function, you can write this as y equals mx plus b, right? Go with this. So on any spring, when you are plotting force and elongation, what is your y-intercept always going to be?
0.
0. Why?
That's the point of origin.
Yeah, Mother Nature's a lazy prima. Mother Nature's going, I'm not going to stretch the spring. Dude, you want to stretch? You do it. I'm not going to. So you know your y-intercept is always going to be 0. Now, what's graphed on your y-axis?
Force.
Force, right? What's the m going to be?
K.
Spring constant, right? And then you're going to have x. Now, sometimes in the book, and I'm pointing this out because your book handles this just a little bit differently on some of those problems. So what are you going to do to find that force? Like, what would you multiply together?
Mass and the gravitational constant.
Yeah, so this is going to be the mass of whatever's hanging down times g, which is going to be k times that. And your book kind of parlays this into delta L. So if the only reason, again, I'm just pointing this out, so if you see this equation in your book, don't flip out and go, oh my God, we've never seen this equation before. Yes, you have, okay? This is just mg, here's your k, this is your change in length. So if you see the book, and you see this equation in your problem, don't flip out and go, oh my God, we've never seen that before. That's how it is, okay? There you go. Now, we need to look at kind of a different perspective on some things. So now we need to tie in angular motion again. Okay?
No.
No, it's okay. It'll be all right. It is. Okay. So let's say that I've got this 1 kilogram mass spinning around. Okay? Now, you kind of got to take a leap of faith conceptually. So here's the question. If all you could see was motion in this direction, let's say you couldn't judge depth, okay? If I had this going around like this, and all you could see was this motion, okay, going like this, what would you see that mass doing?
Oscillator.
You would see it oscillating back and forth like this, right? You would see it over here, basically at like a maximum amplitude, here. You would see it there at the middle, and then you would see it here at the end, and then you'd see it going back and forth like this. So the whole point of this is that if all you could see was this motion in this direction, you couldn't tell if this mass was oscillating back and forth on a spring from an equilibrium point, or if it was going around on a turntable. Okay? You could not tell the difference between the two of them, because all you could see was that it's going, you couldn't tell if it's going back and forth like this, or if it's oscillating. Mathematically and conceptually, we can treat them as the same thing. So, now that you kind of have that visual. So, on page 44 in your book, I want to kind of go over these equations. So again, so you don't flip out.
Should we get out our book or?
No, I've got them written down. You don't need your book for it.
Okay.
Would you quit? This is gonna look random, but at the end, it's all gonna make sense.
All of my essays.
What'd she say?
All of my essays that I've ever written.
At the end, it all makes sense.
In the end,
You
it
should
all
start, you
makes
should
sense.
start one of your senior essays that way. It'd be a good.
Andrew
Just like
was a
my
good
college
man.
application.
swear it's all gonna look
Trust me,
random,
it's
but it all
gonna
makes
sound random, but it's all gonna make sense to me.
The end is the longest.
Well, yeah, it makes sense.
Yeah,
Not
that's the biggest
accepting
lie
it.
in all of physics, people make sense in the end.
That'll win you points from the teacher.
What's the point? What's the point?
We gotta go.
Well, when I was like an English class at K-State, and we had to like read these different essays, and one of them was written by Martin Luther King, and it was like letters from Birmingham jail. And he starts off, as I
I
said, in
have
this
not
prison,
seen that
and
bottom of where.
whatever. And so we had to write like one in class, and the lecture, or the building I was in was called Bluemont Hall. That's where a lot of the education classes were.
Oh no.
And so I started off, as I sit in prison in Bluemont Hall. I didn't get a very good grade. But it was worth a shot, because it was really funny. It was like, wow, okay.
It's creative.
Yeah, I know.
But a cost.
Yeah, I don't recommend that you do that. So, I'm just saying.
Unless you know for sure your professor has a sense of humor.
And she didn't.
Ooh.
Yeah, I found that out later. I thought she did. She didn't.
So you crack jokes before?
Yeah, but I thought it was kind of funny. And, you know, I thought I was this cute little boyish farm boy. He's having no part of it. Yeah.
Wow.
Yeah. Okay, so depending upon what you're given in the problem,
Gosh.
and then here's the equivalence of all three of these equations. So this is on page, I didn't write that down, 244. 444. Okay? So this is this one that you all did in the lab. Okay? All this is a function of position. A is for amplitude, cosine, little t over big T. Okay? Not a big deal. So this is where we kind of had to do some random substitution. So all I did was I said, oh, period is the same as 1 over frequency. So if I substitute 1 over frequency in for period, then this becomes a cosine 2 pi frequency times time. You get the same units, this is just going to be the frequency. Now, so if you look at this, obviously there's two things that are going to be a factor as far as where this thing is. What's your frequency going to be and where you are at that point in time. Now, so this is where you got to go old school, and this is where you can tie this in circular motion. Okay? So this is omega. Here's we got our butt again. So here's radians per second. So this is equivalent to 2 pi times the frequency, or 1 over the period if you want to do that. So if you look at what happens with the units, because remember 2 pi radians are these weird like dimensionless numbers. Okay, we call them radians, but they're really not radians, but we call them radians because it's dimensionless. And so if you look at what happens with the units, omega is always in radians per second. So if you get 2 pi 1 over seconds, which is radians per second, here you end up with this. So what you can do then, if you're given like the fact that it's spinning at so many radians per second, then this just becomes a cosine but t. So this, I'm just doing this to show you that here's this equivalent. So if I've got this spring oscillating back and forth with certain amplitude, okay, hey, I'd go with this. I know what that frequency is, or I know the period or something like this. So with this one, This would be, hey, I know this thing is spinning at so many radians per second. So this equivalent of spinning at radians per second, going around like this, is the exact same idea as saying, oh, here's an oscillating mass going back and forth on the end of the spring. So depending upon what you're given in the problem, here's the approach that you have to take. But conceptually, it's the exact same thing. You're keeping track of where something is as a function of time. And no matter what, you're going to generate the same curve. But it's like, is this thing going around on a spinning disk, or is it oscillating back and forth? It's mathematically, it's treated the same way. Okay? So I just do that so that you don't completely flip out. Okay. Now, we'll do a little bit more voodoo here, not a lot.
Voodoo? I love voodoo.
So now we're going to kind of combine some more things.
You look like half your face is Susan in pain. Are you okay?
I'm fine.
Okay.
I'll be okay, said no one.
I'm fine, said everyone.
I'll be okay, said a dead man.
Don't worry, miss. The dogs are all watching us, except for number one. Number one is
Okay. So if you look at what you're actually able to measure in an oscillating system, Vmax of all the things that you could measure is the most difficult to measure directly, mainly because of the fact that it's continuously changing. Amplitude is easy, okay? So for example, you could set up, if you really wanted to get high tech, you could have this thing oscillating back and forth, you record it on your phone in slow motion, you have a meter stick back behind it, oh wow, here's my maximum amplitude. Velocity is tough because velocity is always changing, okay? And even if you have it in slow motion, since the velocity is always changing, you can't take distance and divide it by time. So to actually get that Vmax, instead of trying to measure it, what we do is we indirectly measure the amplitude in that spring constant and then use that to calculate that Vmax. So all this is I said, okay, I know at these extremes, this is all kinetic energy, this is all potential energy. So then if you go through here and you solve for Vmax, oh, okay, well, I'm going to multiply or divide this side by m, and then I've got a squared. So then, take the square root of all of that, you get a over k over m. So all this is that equation that I gave you on the lab, and at the time you're like, wow, it's magic, okay? This is just where this comes from. So again, you look at what's going to happen with this amplitude. If you double the amplitude, what's that going to do to the Vmax?
doubled.
It'll double it, okay, if you triple it, because this is just a linear relationship. Now, but if you increase the mass of the system, assuming that the amplitude stays constant, if you increase the mass, then what's going to happen to the Vmax?
It's gonna go lower.
It's going to go slower because of the fact that it's going to be like going like in slow motion. Because and that's what we've seen. Because we took that harmonic oscillator that Mia was very keen on, okay, and when there was basically no mass on it, it vibrated really quick, and you had this big Vmax. As we put more and more mass on it, because we didn't change the amplitude, because Mia pushed it to the same amount each time.
I tried.
We didn't change the K value, because that's a fixed value of the spring itself. So the only thing in that situation we could change was that mass, and as that mass became bigger and bigger and bigger, the Vmax became smaller and smaller and smaller, and then that also increased the period and decreased the frequency. So that's where you've got to be able to take one situation and go, okay, how is that going to play out through a couple of different things? Okay, let me see. Now, we can repackage this a little bit more.
chips have cosine or sine waves. Because then you could repackage them again and say these are sine chips, and then actually make a different one with cosine waves and say these are cosine chips.
I like our cosine.
Sine and cosine chips.
It's cool right now.
Tangent chips.
Those would just be.
Yeah, like chip.
No, it looks like an S. S chips.
Cosine
It doesn't even look like.
I don't like cosine. I don't like cosine.
Like, what is this?
So I know what derivatives and integrals are.
Hmm.
I know what interval is.
I don't know why I expected that to be fancier. But I think it's actually. Yeah, I'm pretty sure that wavy chips are sine chips.
Sine tangent chips.
That's a very interesting thumbnail.
Okay, so, with this
Oh
said,
my.
so now, we're even going to do more repackaging of the chips, wave, kettle, fry, whatever you want. So, here's the period of an oscillating spring. You flip it over, here's your frequency, 1 over 2 pi times the square root of k over n, and do the dimensional analysis, prove that it works. So if I multiply this by 2 pi, I get 2 pi f equals the square root of k over n. Okay? So then, if you go way back up here, and this is what I've got up here, so way back up here, omega equals 2 pi f. So since omega equals 2 pi f, we can say, oh, we can substitute that in for 2 pi f and go, oh, this is omega, the so many number of radians per second. Oh, that equals the square root of k over n. So then you can solve this for any number of things. So you can solve this, oh, k equals m but squared. Okay, so if you know that this thing is moving at so many radians per second, this is just another way of finding this value of k. Now, the Vmax in oscillations has an identity crisis because it can equal so many different things. And it can equal 2 pi fa, which is the same thing as but a, okay, because that's radians per second times your amplitude. So this is like meters per second. This would be in meters per second. And since frequency is the same as 1 over period,